Well, g'day flatties and globe defenders, it's Critical Think from Down Under. In this video I'm going to present measurements and evidence that bust these particular flat earth myths. So evidence that will show the earth is not flat. I will measure the curve. I'll show that it's measurably not flat. Perspective is not the imaginary curve. The lateral curve can be measured, and the distance to the horizon is not relevant in this particular case. That one's for you, Travis, which you always insist on us measuring the distance to the horizon, and I'll show in this video why that's not necessary. Well, we'll do a little bit of a recap about what Phuket Word said in a video. He was offering a correction. So this is the correct analysis, even though the diagram is not really a good diagram, but we'll go into that shortly. Let's listen to this.
This person's height doesn't change, and as long as they go away from the observer on a flat surface, then of course they will remain at eye level for the observer. Yeah, but of course, in the eyes of the observer, they will appear to be smaller. So yes, I should illustrate that like this, to represent that particular point, that when we are referring to eye level, someone of the same height goes off into the distance and they will remain at eye level.
So the most important point there is that when somebody goes off into the distance, they remain at eye level. And I do disagree with the way that the diagram is drawn. That is a flat earth way of representing perspective. It is incorrect. It is a very bad way. You don't have to represent perspective in a diagram. The diagram contains the perspective in it itself. All perspective is just a 2D mapping of a 3D space. None of the geometry has changed, so the person really doesn't get small. I know Phuket Word does acknowledge that, but to draw it like that is not correct in my view. So I'm going to draw, this is a perspective diagram. From this diagram we can determine what the angular sizes of the objects in the diagram are. Now I've replaced the person that Phuket Word had in his diagram, I've replaced it with a ship on water. Right, Flatty, so water is level, as you say. Then this same perspective should apply to ships on the water. At anything that is at eye level will remain at eye level. So flat earthers, and particularly Phuket Word, should agree on that. That's a fundamental aspect of how we see. So from this diagram, if you were to draw it to scale, you could actually use a protractor on those angles and measure the angular size of something. But this one's not to scale, but you can see how the perspective is built into this diagram. First of all, this A is the angular size of this ship that's closer. And you can see that A is bigger than B. The ship far away has an angle of B. So when the ship gets further away, it appears smaller. You don't have to draw special perspective lines. This is the perspective built into the diagram. Perspective is just a way of seeing things. It does not change the geometry. So you draw the geometry correctly, like this. Side-on view is just drawing the geometry correctly, and then the perspective automatically comes out of that. No need to account for it, it's already there. So let's just reiterate on that. If a ship is sailing along flat and level water, then the ship will retain the same eye level height to the observer. So let's also look at the scenario where there's not a flat and level surface. So here I have a level surface on the left there, person standing there, an observer is pointing the camera flat and level at this person's head. Now, if this person was to walk down this ramp to the bottom of the ramp, it makes sense that his head will appear to go down because he is going down and eye level is now above his head. Are you following me yet, flatties? So the other thing to note here is that I don't need to know the distance to the top of this ramp in order to determine that this guy over here has gone down a ramp. Just the simple fact that he is lower in elevation is evidence in itself that he has gone down this ramp. There is no need to know the distance to that beginning of that ramp. And here, let's just say the ramp began earlier. It's a less of a slope on the ramp, but it begins earlier and this distance is less. Does it matter? No. Is he still at the same level? Yes. So it doesn't matter where the ramp begins or ends. In order for you to determine that there is some kind of ramp or lowering in elevation is this measurement of the lowering in elevation. Who cares about the shape of the ramp right now? It could be a rounded ramp like that as well. Doesn't matter. Or it could be a gradual slope like that. Just like in the globe Earth model, if there were a gradual slope, then we would observe that this person or ship, if it was a ship on water, it would go down from level. This is the level line there, and then it would go down. Pretty simple. How can you get that wrong? So here's the observation. This is the ship that is on water. According to the flat Earth model, water is level. So as the ship goes away from the observer, not only will it get smaller, but it will also stay level. So whatever you're looking at on the ship should remain at the eye level. So I've taken some positions of this ship just to allow me to estimate the position of the ship at various times. Now the shipping channels are fairly well defined, so we can get a very good estimate of where the ship would be based on these positions and the speed of the ship. Now, I've marked some of these positions on this Google Earth map. Now, my very first observation point is just when the ship is leaving the port. So here's my usual observation point at Woody Point. The ship is leaving the port of Brisbane. Now, it travels in the shipping channel, which goes up this way, and then a fairly straight line from then on over close to Moreton Island. Now, the thing to note here is, and this is very important to note this, that as far as this first observation here and my last one, this is a lateral movement of the ship. We're often asked, by Phuket Word in particular, that if a ship travels from left to right, or in this case from right to left, then we should see evidence of curvature, just the same way as we see evidence of curvature when the ship moves away from us. So in this case we got a bit of a double whammy, because in order for the ship to move from right to left, it must also at the same time move away from us. So note here that from my first observation of the ship, this is an approximate 90-degree angle there. So this is a lateral movement, and we would expect to see a drop of the ship from first position to the last observation position. The red lines here are the second, third and fourth observations that I took. So on a flat Earth, there would be no drop from position 1 to position 4. So, as per the diagrams I have shown, there is no other conclusion. So if the Earth is flat, then these will be level. If they are not level, the Earth is not flat. So this is what this measurement is all about. Now here's my ship, and I've measured number of pixels from bottom to top. There is 710 pixels. Now I've calculated the height of this ship two ways. The first way is by using my camera as a measuring instrument, and I've done this many times before, and if I do the calculations, the height of this ship is 48.2 meters. I've also calculated the height of the ship because it is carrying containers which are a standard size. Now, there are various container sizes, so it's sometimes a little bit difficult to determine the exact size of these containers. But I've done a lot of analysis on this, and I've worked out that the height of these bigger containers here they are 2.9 meter containers. So I have a stack of 4 containers there, which takes up about 171 pixels. So if the height of the ship is 710 pixels there, then we can translate that into meters. We're taking 710 pixels, divide by 171 pixels, and then we multiply that by 4 because we have 4 containers here and 2.9 meters each container. Now it also comes out as 48.2. To be honest, I didn't expect this to be coming out as the exact same figure. I expected there to be a little bit more error than that. But in this case, it just so happens that the container measurement agrees with the camera measurement. So that would mean then, at my observation height of 15 meters, my line of sight on a flat Earth, level line of sight, should intersect the ship around that point. I've also marked some other relevant points, like 26 meters to the top of those containers, 31.6 meters to this little protrusion on the bridge there. But the main one you got to think about is my eye level on a flat Earth would be here at 15 meters. Now I could be out by a meter or two because of the tides, inaccuracy in measuring my elevation, etc., etc. But that is the region where eye level should be. So I've got my auto level, and I'm taking a video at the first observation point. There was quite a bit of breeze on the day, so it's a little bit noisy. My auto level I calibrated the day before. It took me about 2 hours, and I calibrated over a short distance. So it shouldn't be out by very much, a meter or two at the most. But as you can see, the eye level is about 26 meters up the ship. So there you go. Already now, this is evidence and a measurement that shows that the Earth is not flat. Now, Travis, this one's for you. This is a measurement, right? I'm measuring that the Earth is not flat. You say that you don't need to do measurements. Well, the obvious reason for that is that if you do measurements, you'll find yourself this same evidence here that the Earth is not flat. And that would spoil your whole channel, wouldn't it? Anyway, let's go to the next observation point. So already on this one you can see that the ship has sunk down further. We'll go to the next one. Now my eye level is pointing to that top of the bridge there, that little extension, that protrusion, the top of the bridge. So the ship has gone lower in elevation the further away it goes. So this going lower would indicate that the surface is getting lower and lower as the ship goes away. And one more observation. And now you can see the level line is above the bridge. So what I did then is I did some rough calculations based on these observations. Now this yellow column here is actually the geometric drop. This blue column here is the drop that I worked out by counting pixels and working out the approximate distance to the ship, which is this column B here. Now it matches very well with the geometric drop, which tells me I think that my level is pointing a little bit too high. I would expect this to not match because of normal refraction. So while I calibrated my auto level to a short distance, I don't think it's quite right in the long distance, and I have to now work out a way to calibrate it over a long distance, because this here, even though it does match very well, I don't think it should match. But that tells me that I'm pointing, I think it's a little bit too high. So that's not the only thing here. Now you remember the lateral movement of the ship from the first observation point to the fourth observation point. The ship moved laterally from right to left. Now I measured these drops here. So the lateral drop I measured was 17.5 meters. Now I calculated it based on the distance between the first point and the last point on the Google Earth. So that working out the drop, the geometric drop in that distance is 16.7 meters. So it's less than a meter difference. So when you say that there's no lateral curve, I've just measured a lateral curve right there. The drop in a lateral direction matches the observation. So this is very significant, because when you're trying to do this kind of lateral observation, it's very difficult to eyeball it. And this is why people have observed the horizon actually making a curve by compressing the picture side to side. So not only does a lateral curvature being measured via a camera, I've actually measured it here by taking measurements. So when you're trying to eyeball this, do you think that you would notice this 17-meter drop as this ship moves across from one side to the left? No, you wouldn't. In fact, many flat earthers never have. They just say there's no drop. Even I can say that I would have never noticed that drop. But there it is. If you actually measure, do it properly, there is a lateral curve. So Phuket Word's been asking for a lateral curve for a long time, but he's gone about it all the wrong way. Here's a measurement. Remember, explanations are no good unless you have a measurement. And here's my measurement. Okay, so let's see how we did. So These flat earth myths have been busted. Now the earth cannot be flat because the ship lowers in elevation as it moves away. That can't happen on a flat earth. It must stay at eye level. I've been told very often that there's no measurable curve. Yet my measurements show that the ship is travelling over the curve when compared with a curved surface. Perspective is the imaginary curve. Well, no. Perspective cannot make something go below eye level. Something that is already at eye level cannot go below eye level. So I've measured the curve. It's not imaginary. I've measured it. It's there. And then, this one always gets me. And this is a favourite of Phuket words. Is that if the earth was a sphere, then we would be able to see a lateral curve. Well, I've just measured the lateral curve. Therefore, the earth is a sphere. Travis will always come out and say, "Did you measure the distance to the horizon?" Oh, my goodness me. So, I showed that in here, that Travis, no, it's not necessary to measure the distance to the horizon. And in fact, for most of this measurement, the ship hadn't even gone over the horizon. So, there you go. I think flat earth myths busted.